This is IAT806, Lecture 3.4, where we discuss the matrix stack. So where we left off in the previous segment was that we had translated and rotated such that the rectangle that we drew ends up at this location right here, rotated by 45 degrees and translated from the origin by 35. Now, it might be the case that you might wish to follow that by more translations, more rotations, and more drawing, which is fine until you recognize, oh, wait a minute, I need to go back to the origin. So here's the problem. How do I get back to the origin without resetting everything? And the answer is, if you plan to do a lot of translations and rotations, it helps to know about the concepts of push and pop. So what is push and pop? Pushing is a way to say to the graphic system in processing, remember this orientation. And the name of the method that you call is pushMatrix. And the reason why it's called pushMatrix is, first, push means push onto a stack, and its opposite number is popMatrix, to pop off the top of the stack. I'll show an example of pushing and popping, what that means in terms of stacks, in a second. The reason why it's matrix is that all transformations are represented in 2D by a 3x3 matrix of numbers that embody all of transformation, rotation, scale, and other geometric operations. We're not going to show any of the details of what those matrices look like. Just trust us, there's a matrix in the back room representing transformations. So pushMatrix says, take the current state and remember it. And popMatrix says, ignore all the transformation I just completed doing, take me back to the previous state that existed before I executed its matching pushMatrix call. So push to remember an old state, do some transformations, and then pop to take me back to that previous state. So if we want to remember our original orientation, you can imagine doing the stuff we'd just done a moment ago on the previous lecture segment of saying, translate 35, rotate by 45 degrees, drawing the rectangle. That would draw a rectangle here, rotated by 45 degrees. If we then instead preceded that by pushMatrix and followed it by popMatrix, this set of transformations would take place after the pushMatrix, and when we executed popMatrix, it would throw those transformations out. And what that does is put us back in the situation where the origin is at 0, 0, and x increases in value to the right, and y starts at 0 and increases positive values downwards. So this is the state that we would like to be at. And you can push and pop as many times as you want. It's like writing an address for the way things were on a card, putting it on a stack of cards, and every time you push it, you're adding another card to the stack, and every time you pop it, you're taking a card off the stack. So now let's show what that looks like in the processing window. So here, once again, is our little processing program. And what we'd like to do is just run this. And what we see is the situation that we had before, in which the first rectangle that we get is in lighter orange, and that's generated by translating by 35 and drawing that rectangle. So that's the light orange one. And then the dark orange one is drawn next with a slightly different orange color, darker orange color. We rotate it by 45 degrees, and then we draw the rectangle again, and we get it here rotated by 45 degrees. So there's a nice pair of things drawn one on top of the other. Now what I'm going to do is I'm going to paste in code very similar to what we just saw on the slides, but with a little bit of a few differences. First, I'm going to set the fill value to be blue and translate by 40 and 10 instead of 35, and rotate by 65 degrees. And once again, draw exactly the same rectangle as before. So this call that I've highlighted is just the same as this one, and it's just the same as this one down here. So let's run that. And what you can see is now we've got an additional blue rectangle there. It is drawn off to the right by 40 and down by 10, and it is rotated by 65 degrees instead of 45 degrees. The other thing that's very important is we have not disturbed the drawing of the original rectangle, drawn without any rotation, and the 45-degree rotated rectangle that's in darker orange. And you can see it's in the proper place because the light orange one is drawn first, then the blue one occurs on top of it, and you just see a fragment overlapping, and then finally the dark orange one overlaps this blue one. If we take this out again, we just simply get the previous situation with those two things drawn one on top of the other. Put it back in, and once again, I get the blue one in between. Great. So what has happened here is that the pushMatrix call has basically specified to the processing graphics system, store the existing transformation, which was translate by 3535. And I have then translated and rotated, drawn some stuff, and issued the popMatrix call, which throws out the translate and rotate and returns us back to the situation where we had only done the translate by 3535. We then followed that with the stuff we had before of rotating by 45 degrees and drawing another rectangle. Okay, now let's go back to the slides. So, pushMatrix and popMatrix, what they do is they control a stack. So a stack is a formal structure, similar in concept to an array, that stores pieces of information like a stack of plates in a cafeteria or a stack of cards. And the way it is accessed is unlike an array, which is accessed randomly. You can access any location in an array, just give it the proper index. A stack is accessed only by the top of the stack. And the way its access pattern is what is called last in, first out, or LIFO or LIFO. The graphics matrix stack lets you access this stack through calls to pushMatrix, drawing things, and popMatrix. Very rarely do you access the matrix stack directly by setting matrix values. You always access the graphic stack through pushMatrix and popMatrix calls. pushMatrix stores the current transformation state. You can then draw stuff, and popMatrix restores it back to the previous state. One key proviso that you always have to observe is that there must be an equal number of pushMatrix and popMatrix calls. If you have too many pushMatrix calls, then what will happen is if you do those pushMatrices and put popMatrix calls within the draw function, is eventually you'll what's called blow up the stack by pushing too many items on it such that you run out of stack space. Similarly, if you have more popMatrix calls than pushMatrix, you have what's called stack underflow, where blowing stack has a more formal name of stack overflow. And Stack Overflow is the name of a website I'm sure you might be familiar with. In any case, I have, in my 30-odd years of doing computer graphics, have never run out of stack space unless I have had too many pushMatrix calls. And I've never had a stack underflow unless I've screwed something up and had too many popMatrix calls. So there's always enough stack room. And if you're getting a stack overflow or underflow, it's because you've got a mistake somewhere in managing the stack by having too many push or too many pop, depending on which one there's, whether it's overflow or underflow. So let me just illustrate the way a stack looks. First off, processing starts off the graphic system with the origin at the upper left and the X going right and the Y going downwards. When you do a push operation, what that does is take a copy of the top of the stack and put it on top of the stack base. So here we're pushing A. And then you might do some transformations, and then you do push B, and that puts B on top of A, and you push C, and that on top, is put on top of B. When you do pop, what that does is it removes the top item and returns you to the state B. In some implementations of stack, it might also pop might also have a return value, which is the value of C, but in the matrix stack for computer graphics, we don't get a return value from pop. Pop again yields B, takes B off the top of the stack, returns you to state A. Pop again for the third time yields A and removes A from the top, and you're once again back to the stack base. So that's the way a stack works. And if you hear of stacks in other circumstances, say the call stack or things like that, mentioned in passing, perhaps in the course, that's what's going on behind the scenes, is that there's this data structure that maintains this stack behavior that you see here, just like a stack of plates in a cafeteria. So why do we care? Well, one of the reasons why we care is the matrix stack allows us to compose, translate, rotate operations in an organized manner, and allows you to compose the drawing of something like an articulated figure shown in these little robot things down below in a manner that allows you to focus on one thing at a time without having to worry about unwinding and reversing transformations by storing them somewhere. This matrix stack is doing that storage for you and taking care of all of the details. And what I've said in orange is you don't have to remember the math and remember how to reverse transformations that you've already done. Storing things on the matrix stack through pushMatrix, popMatrix does that for you. So that means that you can make a spiral shape and go back to the origin once you do the last popMatrix. When you're doing drawing of these little robots, you would pushMatrix and draw the center, the body of the robot here. Then you translate and rotate to put the at the shoulder location, put your origin at the shoulder location, and then draw the arm. And you translate and rotate to draw this finger, then popMatrix, pushMatrix, and draw this guy, popMatrix and pushMatrix, and draw this guy. And then finally popMatrix go back to this, and popMatrix go back to here, and pushMatrix and translate and rotate to do this arm. You've kind of read that out kind of rapidly, but that's the basic idea. Translate and rotate in order to move to the new location. Do pushMatrix before you do the translate, and then popMatrix to get back to the basic state. And the reason why is it makes the management of all the geometric information much, much more simple. Okay, so that's the end of Lecture 3, Section 3.4, all about the matrix stack. Now I believe you have more than enough information to be able to move ahead with the next queue of assignments in IAT 806.